When Niels Bohr proposed that the atom did not behave like a miniature clockwork machine but instead followed a set of discrete, almost stair-step-like rules, it marked a turning point in the history of science. Before Bohr, classical physics offered a comforting picture of continuity. Movements could be infinitely smooth, energies could change in tiny increments, and nature seemed like a fine mechanism operating on predictable laws. But the early 20th century introduced puzzles that defied this simplicity: the behavior of electrons, the sharp lines in atomic spectra, and the mysterious stability of atoms themselves. Bohr stepped into this confusion with an idea that was simple in its statement, but revolutionary in its consequences. Electrons could exist only in specific energy levels, and they could move between these levels, not through gradual motion but through sudden, quantized jumps. This idea was inspired by Max Planck's work on blackbody radiation, and the notion that energy itself might come in packets. But Bohr took the bold step of applying quantization to the structure of matter. Instead of imagining electrons spiraling endlessly toward the nucleus, as classical physics predicted, he drew a new picture. Electrons occupy defined orbits, each with fixed energy, and they remain in those orbits without radiating energy. This alone solved the long-standing paradox of why atoms do not collapse. But Bohr's framework went deeper, suggesting that stability is not a natural guarantee, but a result of quantized restrictions built into the fabric of the atomic world. In Bohr's view, an electron cannot simply choose any orbit it likes. It is confined to one of a limited set of allowed paths, each associated with a distinct energy value. These paths were not determined by the smooth unfolding of classical motion, but by the inherent rules of quantum theory. This was more than a scientific correction. It was a philosophical rupture. It implied that nature at its most fundamental level behaves not like a continuous wave, but like a series of discrete steps. Energy is not something that slides along a gradient, but something that leaps from one platform to another in sudden, indivisible jumps. Imagine standing in a building where the floors are labeled, separated by defined distances. You can stand comfortably on any one of these levels, but you cannot stand in midair between them. For Bohr, the atomic world operated the same way. Electrons lived on those levels. When they absorbed energy, they jumped to a higher floor. When they emitted energy, they jumped down, releasing light in the exact color corresponding to the difference between the floors. This explanation mapped beautifully onto the observed spectral lines of hydrogen, giving a mathematical clarity to phenomena that had previously been mysterious. The idea that electrons behave this way required a radical rethinking of how scientists viewed particles. In classical mechanics, a particle can have any energy, occupy any position, and transition continuously. But Bohr's electrons could not. The quantized energy levels made them unlike anything described before. They were entities defined not just by motion but by allowed states of existence. This meant that the universe, at its core, had a built-in structure that limited how matter could behave. It meant that the atom was not an accident of nature but an architecture, a set of constraints shaping reality itself. Bohr's model did not merely describe electrons. It explained why atoms emit specific colors of light. When an electron falls from one quantized energy level to a lower one, it releases a photon with an energy equal to the difference between the two levels. This energy corresponds to a specific color. Thus, the bright, sharp lines in hydrogen spectrum reflect the exact energy jumps of electrons. No longer were spectral lines just strange fingerprints of matter. They were evidence of the quantum structure of the universe. Bohr turned a puzzling observation into a window into the inner design of the atom. To understand the significance of this breakthrough, consider how deeply classical physics dominated thought for centuries. Newton had shown that the same laws apply on Earth and in the heavens. Maxwell revealed how electricity and magnetism intertwine in elegant waves. Their theories painted a universe governed by continuity and smooth predictability. But the atomic realm refused to obey these expectations. When researchers examined light emitted by gases, they saw not a continuous rainbow but discrete lines. When they studied atomic behavior, they encountered abrupt changes, strange stabilities, and mysterious thresholds. It was as if the atomic world followed a rulebook entirely separate from the macroscopic world. Bohr recognized that forcing classical ideas onto the atom was like trying to understand the ocean by studying raindrops. The world of electrons demanded new principles that allowed for suddenness, discreteness, and quantization. His theory, rooted in the idea of fixed energy levels, provided the framework needed to understand atomic behavior without leaning on outdated assumptions. It opened the door to quantum mechanics, providing one of the earliest glimpses into a fundamentally different reality hidden beneath the surface of everyday experience. A striking part of Bohr's contribution was the idea that these energy levels were not simply convenient labels, but actual physical states. Electrons do not travel in spirals or get closer and closer to the nucleus. They simply exist in these quantized states. The moment an electron transitions from one state to another, it does so instantaneously, without traversing the space in between. For many scientists, this notion was almost unbelievable. How could something move without moving? How could a particle change its state without passing through intermediate locations? Bohr's answer was that the classical idea of motion did not apply at the quantum scale. The electron did not travel, it shifted. It did not slide, it jumped. This challenged one of the most deeply held assumptions in physics, continuity. In classical thought, all physical processes evolve smoothly over time. But Bohr showed that this is not true inside atoms. Nature makes leaps. It switches, it quantizes. This realization forced scientists to rethink the meaning of causality, the nature of change, and the foundations of physical law. It revealed that the universe is not the uniform machine many believed it to be, but a layered structure where different rules apply at different scales. Bohr's model also gave scientists a way to calculate the energies of electrons using formulas that matched real-world data. The correspondence between theory and observation was so precise that it left little doubt. Reality did not care about classical expectation. The quantized structure of energy was not a mathematical trick, it was a blueprint of nature. This gave Bohr's theory immense weight, transforming it from speculation into scientific fact. Because of this, future researchers built upon his framework, eventually developing the modern version of quantum mechanics. Bohr's insistence on quantized energy levels also showed that the laws governing the microscopic world were not just scaled-down versions of macroscopic laws. They were fundamentally different, requiring new ways of thinking about particles, waves, and forces. For example, Bohr's electron does not radiate energy while staying in a stable orbit. This violated Maxwell's classical electromagnetic theory, which stated that a charged particle in motion must radiate energy. But experiments supported Bohr. Atoms did not collapse. Electrons did not spiral inward. They remained stable. The only explanation was that the rules of electromagnetic radiation did not apply at the quantum scale. This created tension within the physics community, particularly among researchers deeply invested in classical theories. Bohr's ideas were radical because they required abandoning cherished principles, continuity, determinism, and classical intuition. Yet as more experimental evidence accumulated, it became clear that the universe at the atomic level operated according to Bohr's vision, not classical expectations. One of the biggest implications of quantized energy levels lies in the field of chemistry. The behavior of electrons determines how atoms bond, how molecules form, and how reactions occur. Without quantized energy levels, chemistry would collapse into chaos. If electrons could take any energy, atoms would have no stable configurations. Molecules could not hold together. The periodic table would not exist. Bohr's theory showed that the stability and structure of matter arise from the discrete, quantized architecture of electrons. Every shape, every material, every chemical property traces its roots to the allowed energy levels of atoms. This means that the richness of the world, its colors, its textures, its materials exists because electrons cannot take arbitrary energies. The quantized nature of atoms gives rise to the diversity of elements and compounds. It is the hidden language governing the behavior of matter. Bohr's insight revealed that this language is not continuous but discrete, like a cosmic code made of specific, allowed values. Another important dimension of Bohr's theory is its connection to the developing ideas of probability and uncertainty. Although Bohr's 1913 model used circular orbits, the underlying principle that electrons occupy defined energy states paved the way for the later realization that electron behavior must be described by probabilities. Quantum mechanics, built on the foundation Bohr helped establish, replaced the simple orbits with wave functions and probability clouds, yet the core idea remained: electrons can only exist in specific quantized states. This continuity between early quantum theory and modern quantum mechanics shows the lasting power of Bohr's vision. Bohr's concept of quantized energy levels also forced scientists to reconsider what it means to observe and understand nature. If electrons are not allowed to occupy intermediate energies, then the act of observation is limited by the structure of the atom itself. This connects directly to Bohr's later work on complementarity, where he argued that the nature of reality depends on the conditions of observation. But the seed of that idea lies here, in the quantized structure of atomic energy. The observer does not see a continuous unfolding of events, but a series of allowed transitions. Nature does not reveal incremental details. It reveals discrete outcomes. This was deeply unsettling for many, including Einstein, who preferred a reality governed by continuous laws. But Bohr's theory could not be ignored because it worked. It predicted results no classical model could. It explained spectral lines, atomic stability, and energy emission in a way that matched observation. This forced scientists to accept a more complex relationship between theory and reality, where intuition might fail but mathematics and experiment prevail. The quantized nature of atomic energy also had practical consequences. Technologies such as lasers, LEDs, and semiconductors relied directly on electron transitions between energy levels. When electrons move between these levels, they emit or absorb photons with precise energies. These controlled transitions allow for the creation of monochromatic light, electronic switching, and quantum-based technologies. Without Bohr's insight, the technological revolution of the modern world would not exist. Every microchip, every digital device, every photonic tool owes its existence to the understanding that electrons behave according to quantized energy rules. In many ways, Bohr's idea did not just explain atomic behavior. It rewired the scientific view of reality. It showed that the macroscopic world's continuity arises from an underlying layer of discrete behavior. It revealed that certainty is not fundamental but emergent, built upon the statistical behavior of quantum states. It suggested that the world we experience is only one version of reality constructed from countless quantized interactions hidden beneath our senses. Bohr's quantized energy levels also taught scientists humility. They showed that even the most successful theories could reach limits. Classical physics was not wrong, but it was incomplete. Bohr's theory extended our reach into the atomic domain, offering a deeper understanding while reminding us that every model has boundaries. It encouraged future physicists to seek not final answers, but deeper layers of truth. The revolution Bohr ignited did not come with loud proclamations or dramatic experiments. It came with quiet, mathematical precision, theoretical courage, and a willingness to challenge the comfort of classical thinking. Quantized energy levels became the gateway through which humanity entered the quantum age. They transformed physics from a study of observable phenomena into an exploration of fundamental principles. They changed how scientists view particles, energy, and the structure of matter. Today, Bohr's energy levels remain a cornerstone of scientific education, technology, and research. They are the foundation upon which quantum mechanics was built, the key to understand atomic spectra, and the conceptual bridge between classical and quantum worlds. They represent the moment when science stepped beyond intuition and embraced the profound strangeness of the quantum realm. Bohr's first keynote was not merely a scientific insight, it was a shift in worldview. It showed that nature does not conform to human expectations, but instead follows its own rules, hidden, quantized, and extraordinary. The vision that Niels Bohr introduced, with its sharply defined energy levels and sudden transitions, was not just a local correction to atomic theory. It was a gateway to an entirely new landscape of understanding. To grasp the magnitude of this shift, one must imagine what it meant for scientists of the early 20th century, who were raised on the belief that nature operates like a grand clock, smoothly ticking through time. Suddenly, this elegant continuity cracked open. Bohr's model revealed that within every atom, nature behaves not like a flowing stream but like a staircase. Electron energy does not glide, it leaps. States do not blend, they switch. These simple-seeming facts shattered centuries of assumptions and forced physicists to reconsider the very definition of reality. The response to Bohr's idea from the scientific community was a blend of fascination and disbelief. Classical physics, with its smooth curves and predictable patterns, had worked so well for so long that abandoning its principles felt almost like a betrayal. Yet Bohr's quantized orbits matched experimental observations with astonishing precision. For example, the Rydberg formula, which predicted the wavelengths of hydrogen. Spectral lines had been a mysterious numerical pattern long before Bohr. Classical models had failed to explain why these specific wavelengths appeared. But when Bohr applied his quantized energy levels to the hydrogen atom, the Rydberg formula emerged naturally from the mathematics. Suddenly, a puzzle that had existed for decades had a clear explanation. This success made it impossible to dismiss Bohr's ideas as mere speculation. Bohr's model did something profound. It showed that the universe is built from rules that are fundamentally different from the ones we observe on the human scale. It forced scientists to accept that what feels intuitive might not be true at all. On the atomic level, continuity dissolves, certainty evaporates, and motion becomes a series of defined states, rather than a smooth trajectory. This was a revelation that extended beyond physics. It challenged philosophy, logic, and the human desire for clarity. If energy came in discrete packets, what else in nature might be quantized? What else might behave unpredictably, secretly following mathematical rules invisible to everyday experience? The deeper scientists looked, the more they saw that Bohr's idea of energy quantization was not an isolated phenomenon, but a fundamental property of matter. Experiments with X-ray spectra, electrons in metals, and chemical bonding all pointed to the same conclusion. Electrons behave according to quantized laws. No matter how many experiments were conducted, they all echoed Bohr's original proposal. Nature, at its core, did not allow arbitrary energies. It permitted only specific, allowed values. This was not a suggestion. It was a rule embedded in the structure of the universe. As researchers explored further, they began to realize that quantized energy levels were not just a curiosity, but the key to understanding why matter is stable at all. Without quantized energy states, electrons would collapse into the nucleus, atoms would flatten, and the physical world would fall apart. The stability of matter, the fact that objects keep their shape, that molecules hold together, that materials can exist, comes from the quantized architecture Bohr introduced. This stability is not a given. It arises from the invisible staircases built into every atom. These staircases determine where electrons can be, how they interact, and the limits of their energy. Bohr's concept also played a crucial role in the development of quantum mechanics, which emerged during the 1920s as a complete mathematical framework. While Bohr's original orbits were later replaced by probabilistic wave functions, the essential idea of quantized energy levels survived unchanged. Whether electrons are described as orbiting particles or cloud-like waves, the allowed energy states remain the same. This continuity of concept shows how powerful Bohr's insight was. Even as the formalism of physics evolved, the core idea he introduced stayed firmly rooted at the heart of quantum theory. This evolution led to one of the most surprising discoveries in science. Electrons do not truly orbit the nucleus like planets. Instead, they exist in regions of probability. Yet these probability regions, the modern atomic orbitals, follow the same quantized patterns Bohr originally proposed. In this sense, Bohr's theory remains a conceptual bridge between classical intuition and quantum reality. It gave scientists the first workable model of the atom, opening pathways that later theories refined and expanded. Another aspect of Bohr's concept that proved revolutionary was the idea that electrons could absorb or emit energy only when transitioning between allowed states. This principle provided the foundation for devices like lasers, which function by stimulating electrons to emit photons of the same energy in a synchronized manner. Without the predictability of quantized energy levels, the precise, coherent light of lasers would be impossible. In this way, Bohr's theory did not stay confined to blackboards and lecture halls. It became a practical foundation for some of the most important technologies of the modern world. Semiconductors also rely heavily on quantized energy levels. In materials like silicon, Electrons can exist only in certain energy bands. A gap between these bands determines the material's conductivity, and manipulating this gap allows scientists to create transistors, tiny switches that form the building blocks of all digital electronics. Every smartphone, computer, and digital device worldwide operates because electrons must obey the quantized rules Bohr helped uncover. In a sense, Bohr's ideas are not just abstract theories, they are the invisible architecture of the digital age. But the technological impact, while extraordinary, was not the only profound consequence of Bohr's work. His ideas forced scientists to reconsider the nature of observation. If electrons occupy specific energy states, and if the act of measuring them influences their behavior, then the boundary between observer and observed is not as clear as classical physics assumes. Bohr later expanded on this concept with his principle of complementarity, arguing that certain properties, such as the wave-like and particle-like behavior of electrons, cannot be observed simultaneously. The roots of this deep philosophical insight lie in the quantization of energy. If electrons can only exist in defined states, then observation itself must be limited by those states. You cannot see what nature does not allow to exist. This realization introduced a humbling truth. Human understanding of nature is shaped not just by instruments but by the fundamental structure of reality. We are not discovering a universe that behaves continuously. We are uncovering a layered, quantized realm where some information is inherently inaccessible. This changed the scientific method itself, turning physics into a discipline where probabilities rule and certainty becomes the exception rather than the rule. Bohr's idea also had implications for the nature of light. Einstein had shown that light had particle-like properties, and Bohr's model revealed how electrons interact with photons, absorbing and emitting them in precise amounts. This interplay between electrons and light became a cornerstone of quantum electrodynamics, one of the most accurate physical theories ever developed. The quantized energy transitions within atoms provide the basis for understanding how light interacts with matter, influencing fields from spectroscopy to astrophysics. As the quantum revolution unfolded, Bohr's energy levels became a symbol of a deeper truth. Nature is not obligated to align with human common sense. Instead, common sense must evolve to match nature. This transformation is one of the reasons Bohr is considered a philosophical scientist, not merely a technical one. He understood that scientific revolutions require more than equations, they require shifts in worldview. They demand that humans let go of comfortable assumptions and embrace the strangeness of reality. This strangeness became more evident as quantum mechanics matured. Electrons, once imagined as particles orbiting like planets, were now understood as wave-like entities spread out in space. Yet despite this new picture, the quantized energy levels persisted. They were not artifacts of Bohr's model, but essential features of the quantum world. Whether electrons were waves or particles, they could only exist in specific allowed states. This resilience of the concept showed that Bohr had tapped into a fundamental structure of nature. The more scientists studied atoms, the clearer it became that quantized energy levels were universal. They applied not only to electrons but to many physical systems, vibrating molecules, oscillating electromagnetic fields, nuclear energy states, and even the quantum behavior of macroscopic objects under certain conditions. Everywhere scientists looked, they found quantization. The universe seemed to be built on the principle that certain values were allowed while others were forbidden. Bohr's simple hydrogen atom turned out to be a doorway into a general law of quantum organization. The philosophical implications of this were immense. If the universe operates through quantized steps, then the smoothness humans perceive in daily life is an illusion, a macroscopic effect emerging from countless microscopic discontinuities. The certainty we rely on is not fundamental but statistical. Every piece of matter we touch is held together by the quantized rules Bohr helped discover. Every chemical reaction, every color we see, every beam of light, every electrical signal is governed by the invisible dance of electrons moving between allowed energy states. It is difficult to overstate how transformative this idea was. Before Bohr, atoms were mysterious objects, poorly understood and confusing. After Bohr, they became the foundation of a new physical worldview. Scientists could now predict atomic behavior, explain spectral lines, design new materials, and develop technologies based on quantum principles. The atom was no longer an enigma, it was a structured, quantized system. Bohr's influence extended beyond science. His ideas reshaped how thinkers approached questions about knowledge, reality, and observation. If nature behaved in discrete jumps, what did that say about continuity? In other areas like consciousness, perception, or time itself, philosophers grappled with these questions. Inspired by the quantum revolution, Bohr's theory became a symbol of humanity's confrontation with the limits of understanding, a reminder that nature is often far stranger than human expectation. As the years passed, Bohr's model was refined, improved, and expanded by other scientists. Schrödinger introduced wave mechanics, Heisenberg developed matrix mechanics, and Dirac unified quantum theory with relativity. Yet throughout all these advances, the idea of quantized energy remained at the core. These new theories offered deeper mathematical precision, but the structure of energy levels persisted. It became clear that Bohr had not only discovered a useful model, he had discovered a fundamental truth. Even today, more than a century after Bohr published his first atomic model, the concept of quantized energy levels remains central in fields ranging from nanotechnology to quantum computing. These fields depend on manipulating energy states with extraordinary precision. Quantum computers, for example, rely on controlling the energy levels of atoms or superconducting circuits to create qubits, units of information that can be in multiple states at once. This ability to use the quantized nature of energy to process information marks the beginning of a new technological era. The story of quantized energy levels is ultimately the story of a shift in human perception. Before Bohr, scientists believed the universe was a continuous tapestry woven from deterministic threads. After Bohr, they realized the fabric of reality is stitched from quantum knots, each representing a discrete possibility. This shift did not merely expand scientific knowledge, it redefined it. It showed that the universe could not be fully understood through classical logic, and that the deepest truths often require abandoning intuition in favor of mathematical beauty. Bohr's legacy endures because he revealed something essential about the nature of reality. He showed that beneath the smooth surface of the world lies a structured, quantized realm where matter behaves in ways that challenge imagination. He showed that the stability and diversity of the universe emerge from the invisible architecture of energy levels. And he showed that understanding this architecture unlocks not just scientific insight but technological power. The concept of quantized energy levels began as a daring idea. It grew into a theory, then into a revolution, and finally into a cornerstone of modern science. It is a triumph of human curiosity, a testament to the power of imagination, and a reminder that the universe often defies simple expectation. Through Bohr's vision, we learned that reality is deeper, stranger, and more beautiful than anyone had previously believed. When Niels Bohr introduced the idea of complementarity, he was not merely proposing another scientific principle. He was redefining the very framework through which human beings understand reality. The principle arose from a tension that had been growing within physics, a tension between the wave-like and particle-like descriptions of matter and light. Scientists found themselves in a world where the same entity behaved in two fundamentally different ways, depending on how it was observed. This contradiction seemed impossible within classical reasoning. How could light be both a wave and a particle? How could electrons display interference patterns one moment and strike detectors as discrete impacts the next? Something deeper was at play, something that Bohr recognized was not a flaw in nature but a flaw in the human assumptions used to describe it. Complementarity was Bohr's response, a concept so subtle and far-reaching that it changed not only physics but the philosophy of knowledge itself. He argued that the dual behaviors were not contradictions but complementary aspects of a deeper quantum reality. It was not that light switched between being a wave or a particle, it was that both descriptions were necessary to fully understand its nature. Each revealed certain truths, but neither could reveal the entire picture on its own. The act of measurement, the setup of the experiment, the tools used all these played a fundamental role in determining what aspect of reality would appear. Nature was not fixed in the way classical science imagined. It was participatory, shaped by conditions and context. This idea emerged most clearly in the famous double-slit experiment. When electrons or photons pass through two narrow slits, and no effort is made to detect which slit they pass through. The result is an interference pattern on the screen behind a signature of wave behavior. The particles seem to spread out like ripples on water, overlapping and creating bright and dark fringes. But when scientists place detectors to observe which slit each particle passes through, the interference pattern disappears. Suddenly, the electrons hit the screen as individual impacts, like tiny bullets. The wave-like spreading vanishes. Bohr realized that this was not a trick of the experiment, but a revelation that nature itself presents different aspects depending on the form of inquiry. Complementarity became the intellectual pillar that allowed the quantum world to make sense. Bohr recognized that the different behaviors arise not because particles have inconsistent identities, but because human observation is limited by its own nature. To observe a particle's path, one must interact with it, and that interaction disrupts the conditions necessary for observing wave behavior. In other words, what is seen depends on how it is asked. This was not randomness or magic, it was a fundamental structure of reality. The observer, the measuring device, and the phenomenon were not separate entities, they formed an indivisible whole. Bohr's insight went beyond the laboratory. It challenged one of the deepest assumptions of classical science, that there exists an objective reality independent of observation. In classical physics, one could imagine the trajectory of a baseball even if no one watched it. The ball possessed definite properties regardless of measurement. But Bohr showed that this intuition breaks down at the quantum level. Electrons do not have definite trajectories unless the conditions of observation create them. Their wave-like spread exists until it is forced into a particle-like impact by a measurement. Reality, in this sense, is not a fixed landscape waiting to be discovered. It is a dynamic interplay between nature and observer. This did not mean that reality was subjective or arbitrary. Instead, it meant that the structure of quantum systems includes inherent limits on what can be known at any one time. Certain properties exclude others. The more precisely one property is measured, the more blurred the complementary property becomes. Bohr saw this not as a flaw but as a natural consequence of the quantum world's structure. Just as one cannot simultaneously view the front and back of a coin without flipping it, one cannot simultaneously observe the particle and wave characteristics of an electron. Both are real, but they cannot be revealed in a single picture. Many scientists resisted this view, especially Albert Einstein. He believed that the universe must operate according to definite laws, independent of observers. Einstein famously remarked, "God does not play dice." But Bohr had a different perspective. He believed that the universe was not required to follow human expectations. If the quantum world behaved in complementary ways, then human reasoning must adapt. Nature did not need to conform to human logic. Human logic must evolve to reflect nature. Complementarity thus became not only a physical principle, but a philosophical one, redefining the relationship between human inquiry and the natural world. One of the extraordinary aspects of complementarity was how deeply it shifted the meaning of knowledge. Before Bohr, knowledge meant collecting more and more information about a system until its behavior could be fully predicted. After Bohr, knowledge became a layered understanding, where different perspectives revealed different truths, none of them complete on their own. The world could not be captured in a single unified description. It had to be understood through complementary views, each emphasizing different aspects. This idea resonated with the wave-particle duality of matter. Electrons, photons, and other quantum entities behaved like particles when measured in one way, and like waves when measured in another. Bohr understood that these behaviors were not attributes of the particle itself, but expressions of how nature responds to measurement. He compared it to classical analogies. A story could be told as either a series of events or an emotional journey. Both narratives reveal truths, but they cannot be merged into a single description without losing meaning. Complementary descriptions enrich understanding, not contradict it. The brilliance of complementarity is that it remains consistent with experimental results. Every time scientists attempted to force nature into classical categories, the universe pushed back. When they tried to measure the path of a particle through the double-slit experiment, the wave pattern vanished. When they tried to detect interference, the particle-like impacts emerged. No matter how clever the experiment, complementarity held firm. It revealed that quantum systems do not have definite attributes independent of measurement. They have potentialities, tendencies, probabilities, and constraints. Complementarity also guided the development of quantum mechanics as a discipline. Heisenberg's uncertainty principle, which states that certain pairs of properties cannot both be precisely known at the same time, emerged naturally from Bohr's idea. Position and momentum, for example, are complementary. When one becomes sharp, the other becomes blurred. This was not a technological limitation, but a fundamental feature of nature. It meant that the very fabric of reality was woven from relationships, not from absolute values. No particle could possess a precise position and momentum simultaneously. To force precision in one realm meant losing it in another. This realization had profound implications. It meant the world was not deterministic in the classical sense. The future could not be predicted with absolute certainty, only with probabilities. Yet Bohr saw this not as chaos, but as a new kind of order, an order governed by statistical laws rather than fixed trajectories. Quantum mechanics became a powerful predictive tool, not because it provided exact outcomes, but because it described the probability distributions that shape the behavior of particles. Complementarity allowed scientists to understand why certain questions could be asked and others could not, why some properties could be measured simultaneously and others were mutually exclusive. Beyond the laboratory, complementarity offered a new way of thinking about paradox. Instead of seeing contradictions as fatal flaws, Bohr saw them as signs that reality might require multiple perspectives. For example, the idea that electrons could behave like waves and particles seemed absurd to classical thinkers. But Bohr argued that the absurdity lay not in nature but in the assumption that reality must fit a single conceptual mold. The quantum world invited humans to expand their conceptual toolkit, to embrace dualities that classical logic deemed incompatible. Bohr extended the idea of complementarity into broader domains. He suggested that the principle could apply not only to physics but to biology, psychology, and even social sciences. Humans, he believed, often interpret phenomena using mutually exclusive frameworks, yet both are necessary for a full understanding. A biological system can be described in terms of chemical interactions or as a living organism with purpose and behavior. Both descriptions are true, but they belong to different conceptual worlds. In psychology, a person can be understood through behaviorist principles or through subjective experience, two complementary views. Bohr believed that complementarity revealed a general truth about how humans engage with complex systems. The core insight was that no single viewpoint can capture the whole of reality. The world must be understood through a mosaic of partial glimpses, each highlighting different aspects, just as a quantum particle reveals either its path or its interference pattern depending on how it is observed. Human knowledge reveals different facets depending on the tools and frameworks applied. Complementarity also shaped the development of early quantum philosophy. Bohr argued that language itself becomes inadequate to describe quantum phenomena. Classical terms like particle and wave are not literal descriptions of quantum entities. They are metaphors borrowed from everyday experience. Quantum systems are neither particles nor waves in the classical sense. They are something more fundamental, something that exhibits particle-like behavior in one context and wave-like behavior in another. The classical words are shadows cast by a deeper structure. This realization forced scientists to rethink how language shapes understanding. Bohr emphasized that the limitations of human language reflect the limitations of human perception. The quantum world exists beyond these limitations. Complementarity provided a bridge, allowing humans to understand quantum behavior without forcing it into classical categories. The brilliance of Bohr's vision also lies in how gracefully it resolves quantum paradoxes. For example, the wave function, a mathematical entity describing all possible states of a system, seems to collapse into a definite outcome during measurement. Many found this collapse mysterious, but Bohr explained that the wave function is not a physical wave, but a tool for predicting probabilities. When a measurement occurs, the observer chooses a complementary framework, and the system reveals the corresponding property. The wave function does not physically collapse, the context changes. Complementarity eliminates the paradox by showing that different experimental conditions create different manifestations of the same underlying system. As the quantum revolution expanded, complementarity became a cornerstone of quantum interpretation. It influenced particle physics, quantum field theory, and even emerging debates about quantum information. In quantum computing, qubits exist in superpositions, combinations of states, that cannot be described using classical logic. The act of measuring a qubit forces it into a definite state, reflecting complementarity at the heart of computation. The power of quantum computing arises from exploiting these complementary states before measurement collapses the system. Complementarity also reshaped how scientists understood causality. Classical physics is built on the idea that causes lead to predictable effects, but in the quantum world, probability distributions govern outcome. Bohr proposed that causality at the quantum level is not linear but relational. Events do not unfold in a chain of deterministic steps, they unfold through interactions defined by complementary properties. This introduced a new kind of causality, one that incorporates uncertainty as a fundamental component, rather than a mere lack of information. By embracing complementarity, Bohr transformed physics into a science of relationships, constraints, and possibilities. He showed that understanding the universe requires humility, a willingness to accept that human intuition is limited, and that nature may operate on principles beyond everyday experience. Complementarity became a symbol of this humility, a reminder that truth often lies in multiple perspectives, not in a single, absolute description. The principle opened doors to new interpretations of everything from reality to consciousness. Scientists began to explore whether complementarity might play a role in how information is processed in the brain, or how biological systems maintain order. While these ideas remain speculative, they reflect the depth of Bohr's insight. The quantum world is not isolated from human experience, it shapes the foundations of the universe we inhabit. Complementarity remains one of the most powerful and profound ideas in science. It explains why quantum mechanics cannot be forced into classical frameworks, why particles behave like waves under one condition and like particles under another, and why certainty dissolves into probability in the atomic realm. It reveals a universe where knowledge is contextual, where reality depends on interaction, and where truth is a tapestry woven from complementary strands. The world at the beginning of the 20th century was brimming with discoveries, yet it was simultaneously baffled by mysteries that refused to fit into the neat framework of classical physics. Spectral lines appeared in the light emitted by atoms, revealing precise colors that could not be explained by the continuous motion of electrons. Radioactive decay and the behavior of subatomic particles hinted at forces and rules far stranger than the predictable laws that governed the macroscopic world. Amid this turmoil, Niels Bohr emerged with a daring vision to construct a model of the atom that could reconcile observed phenomena with theoretical consistency, even if it required a radical departure from centuries of classical reasoning. Bohr's atomic model was revolutionary in its audacity. He did not merely refine the existing picture, he challenged its very foundation. Classical physics, rooted in the ideas of Newton and Maxwell, imagined electrons as tiny planets orbiting a central nucleus, their paths determined by smooth, predictable forces. But such a picture failed dramatically when confronted with reality. According to classical electromagnetism, an electron circling a nucleus would radiate energy continuously, spiraling inward, and collapsing the atom in a fraction of a second. Yet matter remained stable. Chemical reactions occurred in predictable patterns, and spectral lines persisted in precise arrangements. Bohr recognized that to explain these phenomena, a new framework was necessary, one that combined the empirical successes of observation with an innovative theoretical structure. Central to Bohr's model was the concept of quantized energy levels. Electrons do not orbit in arbitrary paths. They occupy discrete shells or energy states around the nucleus. Each level corresponds to a specific area, and electrons can jump from one level to another, absorbing or emitting a quantum of energy in the process. This principle elegantly resolved the paradoxes that had long perplexed physicists. The atom remains stable because electrons in a given energy state do not radiate energy. The spectral lines, once inexplicable, became clear evidence of these quantum jumps. Each line represented a photon emitted or absorbed as an electron transitioned between quantized levels. Bohr had turned a set of mysterious experimental observations into a coherent theoretical framework. What made Bohr's model particularly compelling was its predictive power. By applying quantized orbits to the hydrogen atom, he was able to derive the precise wavelengths of its spectral lines using mathematical relationships. This was not an approximate fit. The model matched experimental data with astonishing accuracy. For the first time, the behavior of atoms could be calculated and predicted, rather than merely described after the fact. It was a triumph that combined bold conceptual leaps with rigorous quantitative analysis, and it immediately captivated the scientific community. Bohr's approach was marked by a unique blend of pragmatism and philosophical insight. He was willing to abandon classical visualizations where they failed, yet he retained the principle that physical theories should connect with observable phenomena. Electrons could not be pictured as tiny planets following smooth trajectories, but they could be understood in terms of their energy states and the transitions between them. This marked a profound shift in scientific thinking. The focus was no longer solely on picturing the atom but on describing its measurable properties and predicting its behavior with precision. It was a move toward abstraction without losing empirical grounding. The implications of Bohr's model extended far beyond the hydrogen atom. Once the concept of quantized energy levels was established, it could be applied to more complex atoms, chemical reactions, and even emerging technologies. Understanding how electrons occupied specific shells allowed chemists to explain the periodic table in terms of electron configurations, predicting the chemical properties of elements based on the arrangement of electrons. This bridged a gap between physics and chemistry, showing that atomic theory was not merely an academic exercise but a foundation for understanding the material world. Bohr's vision connected the microscopic rules governing electrons to the macroscopic phenomena observed in laboratories and industry. At the heart of Bohr's contribution was an insistence on experimental consistency. He did not simply invent quantized orbits because they were elegant. He introduced them to explain stubborn, repeatable phenomena. Spectral lines, atomic stability, and electron behavior all demanded a model that matched observation. Bohr's genius lay in recognizing that nature's behavior at the atomic level required principles that differed from classical expectation. This was not a rejection of physics as a discipline but an extension of it, a recognition that the classical rules were incomplete rather than wrong. Bohr's model also laid the foundation for the quantum revolution. It introduced the notion that certain quantities, like energy, are discrete rather than continuous. This quantization challenged centuries of assumptions and required scientists to rethink the very nature of matter and light. The atom was no longer a small-scale replication of the macroscopic world. It was governed by its own rules, revealing a new layer of reality. This shift catalyzed the development of quantum mechanics, which would expand and formalize Bohr's ideas, explaining phenomena from electron spin to wave-particle duality, from chemical bonding to nuclear forces. One of the most profound effects of Bohr's model was its philosophical impact. By showing that electrons occupy discrete states and that observation affects the properties revealed, Bohr highlighted the limitations of classical determinism. Nature at its core was not a clockwork universe, it was probabilistic and contextual. The model implied that knowledge itself had limits. One could predict probabilities and outcomes with precision, but absolute certainty about every aspect of a quantum system was impossible. This challenged the scientific worldview that had dominated since Newton and forced physicists to reconsider the assumptions underlying their theories. The educational impact of Bohr's atomic model cannot be understated. For students of physics and chemistry, it became a gateway into the world of quantum thought. By introducing quantization in an accessible and mathematically rigorous way, Bohr provided a stepping stone to more advanced theories. Schrödinger, Heisenberg, and Dirac would build on this foundation, but the conceptual leap, the willingness to replace smooth orbits with discrete energy states, originated with Bohr. His model served as both a tool for calculation and a lens for understanding the invisible architecture of matter. Bohr's atomic model also transformed experimental science. Spectroscopy, previously a descriptive field, became a precise, quantitative tool. By understanding energy levels, scientists could predict the wavelengths of light emitted or absorbed by atoms. This predictive capacity accelerated discoveries in chemistry, astronomy, and materials science. The colors of stars, the behavior of gases under high energy, and the properties of newly synthesized elements could all be interpreted through the framework Bohr provided. The model unified observation and theory in a way that had rarely been achieved in the history of science. The introduction of quantized energy levels also gave rise to a new understanding of light-matter interaction. When electrons transition between energy states, they absorb or emit photons, with energies precisely matching the difference between levels. This concept became fundamental to later developments in quantum electrodynamics, lasers, and semiconductors. Without Bohr's insight into atomic energy states, technologies such as LEDs, photovoltaic cells, and quantum communication devices might never have emerged. The practical applications of his theory demonstrate that what began as a theoretical framework quickly became a foundation for technological innovation. Bohr's model emphasized the inseparability of theory and experiment. He repeatedly stressed that concepts in quantum physics must be grounded in measurable phenomena. Hypothetical constructs without experimental support were insufficient. A theory's validity was determined by its ability to predict observable outcomes. This principle guided not only his work but also the subsequent development of quantum mechanics. The balance between abstraction and empirical evidence became a hallmark of modern physics, shaping the methodology of countless researchers and laboratories. One of the subtle but profound aspects of Bohr's approach was the recognition of limits. He understood that no single model could capture the entirety of atomic behavior. While the planetary-like model with quantized orbits was effective for hydrogen, more complex atoms would require additional principles and refinements. This humility in scientific modeling, acknowledging the scope and limitations of one's framework, was a key factor in the robustness of Bohr's contribution. It encouraged an iterative, evidence-driven approach to theory building that would characterize quantum mechanics in the following decades. The theoretical elegance of Bohr's model also lay in its mathematical simplicity. By introducing quantized orbits with specific radii and energy levels, he created a model that was computationally tractable while remaining physically meaningful. This allowed scientists to make predictions and compare them with experiments, reinforcing the theory's credibility. It bridged the gap between the abstract world of numbers and the tangible reality of atomic phenomena, demonstrating that mathematical beauty could align with empirical truth. Bohr's atomic model reshaped the way humanity perceives the microcosm. It revealed that beneath the apparent solidity of matter lies a dynamic, quantized realm where electrons leap between defined states, light emerges in discrete packets, and observation shapes the reality that is revealed. This was not merely a correction to previous theories, it was a profound transformation in understanding. The atom was no longer a passive, mechanical entity but an active participant in a universe governed by rules that defied classical intuition. The success of Bohr's model inspired further exploration into atomic and subatomic physics. The discoveries of spectral lines and other elements, the identification of isotopes, and the understanding of chemical bonding all drew upon the principles established by Bohr. The atomic nucleus, electron clouds, and quantum interactions became subjects of study, each revealing complexities that his model hinted at but did not fully resolve. His work provided the scaffolding upon which the quantum revolution would be constructed. In addition, Bohr's vision encouraged scientists to think probabilistically. Whereas classical mechanics emphasized precise prediction, the atomic model required acceptance that only certain outcomes could be predicted, and only in terms of probabilities. Electrons occupy allowed states, but their exact position at any moment is uncertain until measured. This probabilistic perspective was a radical departure from centuries of deterministic thinking and became a defining characteristic of quantum mechanics. Bohr's atomic model also emphasized the unity of physical laws by showing that the same principles governing energy transitions in a hydrogen atom could be extended to more complex systems. He highlighted the coherence and universality of quantum behavior. Patterns emerged across the periodic table, across chemical reactions, and across atomic spectra, revealing a hidden order within the apparent chaos of the microscopic world. Bohr's insight was that the quantum rules, though counterintuitive, were universal, forming a consistent framework that explained the structure and behavior of matter. At its core, the atomic model represented a paradigm shift in science. It demonstrated that the universe at small scales is not a scaled-down version of the macroscopic world, but operates according to fundamentally different principles. Smooth motion, continuous energy, and deterministic paths give way to discrete jumps, quantized states, and probabilistic behavior. Bohr's vision transformed the human understanding of reality, showing that the microcosm operates in ways that challenge intuition yet remain rational, predictable, and mathematically describable. Bohr's work also underscored the importance of daring hypotheses in science. He did not wait for the perfect solution. He proposed a bold, testable model that explained existing phenomena and predicted new outcomes. This courage to challenge conventional wisdom while remaining grounded in empirical evidence is a hallmark of scientific genius. Bohr's atomic model is as much a story of intellectual audacity as it is of scientific precision. The far-reaching implications of Bohr's model are still felt today. From spectroscopy and chemistry to quantum computing and photonics, the principles he introduced continue to underpin technological progress. The quantized energy levels, electron transitions, and interaction of matter with light remain foundational concepts. Modern research in nanotechnology, quantum information science, and condensed matter physics relies on the framework he established more than a century ago. Bohr's vision, once revolutionary, has become indispensable. The atomic model's enduring power lies not just in its predictive success, but in its conceptual clarity. It shows that nature, while complex, is not arbitrary. The behaviors that seemed mysterious, spectral lines, atomic stability, electron emission, are manifestations of deeper principles. By articulating these principles, Bohr transformed the atom from an abstract curiosity into a coherent, understandable system. This achievement exemplifies the interplay between observation, theory, and imagination that defines the best of scientific inquiry. The second half of the story of Bohr's atomic model reveals just how deeply it reshaped both scientific practice and the broader understanding of reality. The model's implications were not confined to explaining hydrogen or matching spectral lines. They rippled outward into every field that interacts with the quantum world. Bohr had constructed a bridge from observation to principle, from empirical fact to theoretical structure, and across that bridge, generations of scientists would travel to explore the vast, strange territory of the microscopic universe. One of the most immediate consequences was the way Bohr's model redefined chemical behavior. For centuries, chemists had organized elements by empirical patterns, noting similarities in properties and reactions. Mendeleev's periodic table, for example, arranged elements according to atomic mass and observed chemical characteristics. But why did these patterns exist? Bohr's atomic model provided a mechanistic explanation. The arrangement of electrons in quantized orbits dictated chemical properties. Atoms with similar outer electron configurations exhibited similar reactivity. This insight not only validated the structure of the periodic table, but also provided a predictive framework for chemistry, allowing scientists to anticipate properties of elements yet to be discovered. Chemistry, which had long relied on patterns derived from observation, suddenly had a firm foundation in fundamental physics. Bohr's model also revealed the critical role of energy quantization in physical stability. Classical physics had suggested that atoms should collapse as electrons radiated energy while orbiting the nucleus. Yet, Bohr's model explained why this does not happen. Electrons in quantized orbits cannot lose energy continuously, and thus atoms remain stable. The very solidity of matter, the persistence of materials around us, and the existence of life itself depended on these invisible, rule-bound energy levels. This insight was both humbling and revolutionary. Stability, it turned out, was not a given. It was an emergent property rooted in quantum rules. It was as if Bohr had uncovered the scaffolding of reality, showing that the durability of the material world is a consequence of discrete, invisible structures. Another profound implication of Bohr's atomic model was the recognition that measurement and observation are intertwined with the nature of the quantum system. When electrons jump between energy levels, they emit or absorb photons. The act of detecting these photons reveals the transitions and energy differences. The very properties of the atom become meaningful only through interaction with observation tools. This principle laid the groundwork for future developments in quantum mechanics, particularly the Copenhagen interpretation, which Bohr himself championed. The model implied that nature cannot be fully described independently of the measurement context. In this sense, Bohr's atomic model was not only a structural framework for the atom, It was a guide to the philosophical landscape of quantum reality, demonstrating that reality is relational, not absolute. The predictive success of Bohr's model also accelerated experimental physics. Spectroscopy, once a tool for cataloging unknown emission lines, became a quantitative science. By understanding electron transitions, scientists could predict the wavelengths of light emitted or absorbed by atoms. This precision enabled the analysis of stellar compositions, the identification of new elements, and the development of devices such as gas discharge lamps and later lasers. Bohr had transformed atomic theory from a descriptive framework into an instrument for exploration and technological innovation. The model demonstrated that theoretical insight could directly drive experimental progress. As the quantum revolution unfolded, Bohr's atomic model inspired the development of more sophisticated theories. Schrödinger's wave mechanics offered a new way to describe electron behavior, treating electrons as wave-like entities spread across space. Heisenberg's matrix mechanics formalized the probabilistic nature of quantum observables. Yet, in all of these developments, the principle of quantized energy levels remained central. Bohr's original insight that electrons occupy specific energy states proved remarkably resilient. Even as the mathematical formalisms became more abstract, the conceptual heart of Bohr's model persisted. It was a testament to the robustness of his vision. A simple idea, deeply understood, could anchor a complex and rapidly evolving theoretical landscape. Bohr's model also reshaped the understanding of light-matter interactions. Electron transitions produce photons with energies corresponding precisely to the energy difference between levels. This principle underpins modern technologies, ranging from lasers to LEDs, from photovoltaics to quantum communication devices. The emission and absorption of light, once mysterious and unexplained, now had a precise theoretical explanation. In this sense, Bohr's atomic model was not a theoretical curiosity. It became the foundation for entire technological industries. The ability to manipulate electrons and photons with precision owes its roots to the quantized orbits he proposed. Moreover, Bohr's model introduced a new way of thinking about the probabilistic nature of physical systems. Classical physics emphasized deterministic outcomes. Given initial conditions, future behavior could be predicted exactly. Bohr's atom suggested a different approach. The energy levels and transitions implied probabilities rather than certainties. While an electron may occupy a specific energy state, its position and momentum cannot both be known with absolute precision, a concept formalized later by Heisenberg's uncertainty principle. Bohr's insight into quantization thus planted the seeds for the recognition that the universe at its core is probabilistic, governed by likelihoods and potentialities rather than rigid determinism. This probabilistic perspective had far-reaching philosophical consequences. It challenged centuries of belief in a predictable, clockwork universe. Nature, Bohr suggested, is not obligated to conform to human intuitions about continuity or causality. The atomic world operates according to principles that are precise yet non-intuitive, discrete yet interconnected. Bohr's model provided the first concrete framework to grapple with these ideas, demonstrating that a universe could be orderly, lawful, and predictable in its probabilities, even while defying classical expectation. The atomic model was both a scientific and a philosophical milestone, marking a turning point in humanity's understanding of reality itself. Bohr's atomic model also had profound implications for chemical bonding. By explaining electron arrangements and allowed energy levels, it provided insight into how atoms combine to form molecules. Covalent bonds, ionic interactions, and the structure of complex molecules could be understood in terms of electron transitions and configuration. This unification of atomic theory with chemical principles created a cohesive scientific narrative linking the microcosm of electrons to the macroscopic world of materials, reactions, and biological processes. Chemistry became a direct extension of atomic physics, and Bohr's model was the bridge connecting the two domains. In addition, Bohr's model highlighted the importance of visualization in scientific reasoning. While electrons could no longer be pictured as planets orbiting the nucleus, the concept of discrete energy levels provided an intuitive scaffold for understanding atomic behavior. Students and researchers could imagine electrons jumping between shells, absorbing or emitting photons, without requiring an exact physical trajectory. This balance between conceptual visualization and mathematical rigor became a hallmark of Bohr's approach. He demonstrated that scientific insight often requires a synthesis of imagination and calculation, of metaphor and measurement. Bohr's work also emphasized the iterative nature of scientific progress. His model was not the final word on atomic structure. It worked exceptionally well for hydrogen, but for multi-electron atoms, additional principles and refinements were necessary. This humility, acknowledging the limits of a model while appreciating its explanatory power set, a standard for scientific methodology. It illustrated that models are tools, evolving and adapting as new data and theoretical insights emerge. Bohr's atomic model exemplified how science advances through bold hypotheses, rigorous testing, and continuous refinement. The model's influence extended into modern physics, guiding explorations of nuclear phenomena, particle interactions, and quantum information science. Understanding the atom as a system of quantized energy states became foundational for research into atomic nuclei, subatomic particles, and the interactions that govern them. The principles introduced by Bohr continue to inform experimental design, theoretical development, and technological innovation across multiple fields. Without the atomic model, modern quantum physics would lack the conceptual foundation necessary to describe the behavior of matter and energy at fundamental scales. Bohr's atomic model also encouraged a reconsideration of the relationship between theory and experiment. The model demonstrated that theoretical proposals must be rooted in observable phenomena, yet also that theory can guide experimentation. Spectroscopy, chemical analysis, and later quantum technologies all benefited from this feedback loop. Bohr's vision illustrated that progress in science requires a dynamic interplay between what is observed and what is hypothesized, between empirical evidence and conceptual imagination. The introduction of quantized energy levels also transformed the understanding of photons and the nature of light. Once described purely as a wave, now had a particle-like aspect intimately connected to electron transitions. This duality, wave and particle, emerged naturally from Bohr's model, foreshadowing the broader principle of wave-particle duality in quantum mechanics. Bohr's insight into energy levels provided the experimental and conceptual framework to reconcile these dual aspects, demonstrating that light's behavior is context-dependent and governed by the same discrete principles that structure matter. In education, Bohr's atomic model became an essential teaching tool. It provides students with a conceptual bridge from classical to quantum thinking, illustrating how scientific understanding evolves in response to evidence. By introducing quantized orbits, discrete energy states, and electron transitions, Bohr's model allows learners to grasp the principles underlying atomic behavior before engaging with the full complexity of modern quantum mechanics. It remains a cornerstone of physics and chemistry curricula worldwide, emphasizing the importance of foundational models in shaping scientific literacy. Bohr's atomic model also influenced emerging technologies in unexpected ways. Semiconductors, lasers, and quantum dots all rely on the principles of quantized energy levels. Understanding how electrons occupy discrete states, absorb energy, and transition between levels enables precise manipulation of matter at the nanoscale. The modern information age, with its reliance on electronics, computing, and photonics, can trace its origins to the conceptual framework Bohr introduced over a century ago. The atomic model thus represents not only a scientific breakthrough but a technological enabler, linking theory to application in profound and tangible ways. The model's elegance lies in its synthesis of simplicity and depth. On the surface, the idea of electrons in discrete orbits seems straightforward, even intuitive. Yet the consequences of this concept extend to the deepest questions of quantum behavior, measurement, and the nature of reality. Bohr's insight demonstrated that a single conceptual leap could illuminate a vast range of phenomena, from spectral lines and chemical bonding to wave-particle duality and quantum uncertainty. This duality of simplicity and profundity is a hallmark of transformative scientific ideas. Bohr's atomic model also set the stage for debates that would define the philosophical landscape of quantum mechanics. Questions about determinism, observation, and the role of the observer in shaping reality all emerged naturally from the model's principles. These discussions, which involved Bohr, Einstein, Heisenberg, and others, underscored that scientific theories are not only descriptive tools but also frameworks that shape our understanding of existence itself. Bohr's atomic model thus bridges physics and philosophy, illustrating that the quest to understand matter is inseparable from the quest to understand knowledge and reality. In summary, Bohr's atomic model represents one of the most consequential intellectual achievements of the 20th century. By introducing quantized energy levels, explaining spectral lines, connecting atomic structure to chemical behavior, and laying the foundation for quantum mechanics, it transformed science. Its implications are philosophical, technological, and educational, influencing how humans understand the microscopic world and how they interact with it through experimentation and innovation. Bohr's vision revealed that the atom is not a miniature solar system, but a quantum system governed by discrete rules, probabilistic transitions, and profound order beneath apparent complexity. The model remains a cornerstone of modern science, a testament to the power of imagination guided by observation, and a foundation upon which the quantum revolution was built. Niels Bohr's influence on modern quantum thought extends far beyond the construction of his atomic model. It lies in the philosophical and methodological frameworks he introduced, frameworks that shaped the very way scientists approach the quantum world. Bohr was not content with providing formulas and predictions. He sought to fundamentally redefine the relationship between theory, observation, and reality. At a time when physics was grappling with anomalies that classical mechanics could not explain, Bohr emerged as both a theorist and a philosopher, recognizing that the mysteries of the subatomic world required more than incremental adjustment. They demanded a shift in how knowledge itself was conceived. He introduced a perspective in which the observer and the observed could no longer be considered entirely separate, where the conditions of measurement shaped the phenomena revealed, and where certainty gave way to probabilities. This was a radical departure from centuries of scientific thought, and one that positioned Bohr as the architect of a new quantum paradigm. Bohr's approach emphasized the principle of complementarity, which allowed scientists to reconcile seemingly contradictory observations. In classical thinking, phenomena were expected to possess intrinsic properties that existed independently of measurement. In the quantum realm, however, electrons and photons revealed themselves differently depending on the experimental setup. Bohr recognized that these dualities were not flaws or paradoxes, but necessary aspects of a deeper reality. By framing these behaviors as complementary rather than contradictory, he provided a conceptual lens through which the quantum world could be understood. This perspective not only explained experimental results, but also guided the development of quantum theory, offering a philosophical foundation for interpreting outcomes that defied classical logic. Bohr's role in shaping modern quantum thought was also evident in his mentorship and collaboration with leading physicists of his time. His institute in Copenhagen became a hub for some of the greatest minds of the era, including Werner Heisenberg, Wolfgang Pauli, and Max Born. Bohr fostered an environment where rigorous debate, imaginative theorizing, and experimental testing coexisted. He encouraged young scientists to challenge assumptions, to consider the philosophical implications of their models, and to embrace the counterintuitive nature of the quantum world. Through these interactions, Bohr transmitted not only technical knowledge but also a mindset, an approach to thinking about reality that combined precision, creativity, and humility. This intellectual culture played a crucial role in the rapid development of quantum mechanics, turning Copenhagen into the epicenter of a revolution in physics. Central to Bohr's contribution was his insistence that the laws of quantum mechanics were universal, yet fundamentally different from classical laws. He emphasized that atoms, particles, and waves could not be fully described by classical analogies, and that attempts to force them into familiar frameworks would yield contradictions. By embracing this new conceptual structure, scientists were able to develop theories that accurately predicted phenomena such as spectral lines, particle scattering, and electron transitions. Bohr's insistence on the independence of quantum principles from classical intuition allowed researchers to explore domains that had previously been inaccessible, providing the foundation for technologies such as semiconductors, lasers, and quantum computing. In this way, his ideas not only advanced theory, but also laid the groundwork for practical applications that continue to shape the modern world. Bohr's philosophical insight extended to the interpretation of measurement itself. He argued that the act of observing a quantum system is inseparable from the system being measured, a notion that challenged long-held assumptions about objectivity in science. This realization led to the Copenhagen interpretation, which posits that quantum entities do not possess definite properties until they are observed, and that reality at the quantum level is intrinsically probabilistic. Bohr's reasoning emphasized that knowledge is not merely about discovering pre-existing facts, but about understanding the conditions under which phenomena manifest. This approach demanded a new epistemology, one that accepted limits on what could be known, and that embraced probability and uncertainty as fundamental characteristics of nature. The philosophical courage required to adopt such a view underscores Bohr's role not only as a physicist but as a thinker who reshaped the boundaries of human understanding. The debates between Bohr and Albert Einstein illustrate the depth of his impact on modern quantum thought. Einstein, seeking determinism and objective reality, challenged Bohr on the completeness of quantum mechanics. Bohr, in response, defended the consistency and necessity of complementarity and probabilistic interpretation, demonstrating that classical expectations were insufficient for describing atomic phenomena. These debates were not merely academic exercises, they highlighted the profound conceptual shifts required to understand the quantum world. Bohr's ability to articulate and defend these ideas solidified the philosophical foundation of quantum theory, influencing generations of physicists who followed. Bohr also emphasized the interconnectedness of theory and experiment, insisting that models must be grounded in measurable phenomena. He recognized that abstract mathematical formulations alone were insufficient; they had to correspond to observable outcomes. This principle guided both theoretical developments and experimental design, fostering a pragmatic approach that combined rigorous mathematics with empirical verification. The result was a quantum framework that was internally consistent, predictively powerful, and experimentally testable, a hallmark of modern physics. By insisting on this balance, Bohr ensured that quantum theory would not remain an abstract speculation but would evolve into a robust scientific discipline. Furthermore, Bohr's ideas influenced the emerging field of nuclear physics, providing insights into the structure and behavior of atomic nuclei. His understanding of quantization, energy levels, and wave-particle duality informed models of nuclear decay, particle interactions, and the forces governing subatomic systems. The theoretical scaffolding he provided allowed subsequent researchers to explore phenomena at increasingly smaller scales, paving the way for the discovery of protons, neutrons, and later quarks. Bohr's conceptual clarity thus extended beyond atomic theory, shaping the trajectory of the entire field of particle physics. Bohr's role in shaping modern quantum thought also had educational implications. He developed a method of presenting quantum concepts that bridged intuition and abstraction, allowing students and researchers to grasp counterintuitive ideas without abandoning logical rigor. By introducing models, thought experiments, and conceptual frameworks, Bohr facilitated a deeper understanding of quantum principles, fostering a generation of physicists capable of navigating the complexities of the quantum world. His influence persists in textbooks, lectures, and the pedagogy of physics, ensuring that his approach continues to shape how knowledge is transmitted. Ultimately, Bohr's contributions represent a synthesis of scientific insight, philosophical depth, and methodological innovation. He transformed the understanding of the atom from a mechanical construct into a quantum system governed by discrete laws, probabilistic outcomes, and relational properties. His work bridged the gap between observation and theory, guiding scientists to interpret experimental results within a coherent, albeit non-classical, framework. By doing so, he not only advanced physics but also reshaped the way humanity conceives of reality, demonstrating that the smallest constituents of matter reveal profound truths about the nature of knowledge, measurement, and the limits of human understanding. Bohr's legacy in modern quantum thought is therefore multidimensional. He provided a robust theoretical foundation for quantum mechanics, introduced philosophical principles that clarified the interpretation of experimental results, fostered a collaborative and intellectually daring research culture, and influenced educational and technological developments for generations. His vision of the quantum world, where observation, measurement, and probabilistic laws converge, remains a guiding framework for contemporary physics. Bohr's role was not merely that of a scientist producing formulas. He was a thinker who rewired the conceptual landscape of reality, showing that understanding the quantum universe requires imagination, rigor, and a willingness to embrace principles that transcend classical intuition. In essence, Niels Bohr's impact on modern quantum thought is inseparable from his ability to integrate empirical observation with conceptual innovation. By redefining the relationship between measurement, theory, and reality, he provided the intellectual scaffolding for the quantum revolution. His insights into complementarity, probabilistic outcomes, and the limitations of classical analogies continue to resonate, influencing physics, philosophy, and technology alike. Bohr's work demonstrates that transformative scientific thinking emerges not only from technical skill but also from the courage to challenge foundational assumptions, to accept paradox, and to construct coherent frameworks that illuminate the hidden structures of nature. His legacy endures as a testament to the power of conceptual audacity and the enduring quest to understand the fundamental workings of the universe. Niels Bohr's influence on the development of quantum mechanics and the broader philosophy of science was profound and multifaceted. His contributions went beyond the specific details of atomic structure. They shaped the conceptual foundations upon which modern physics was built. Bohr's work exemplified the interplay between observation, theory, and philosophical reflection, showing that understanding the quantum world requires more than technical calculations. It demands a rethink of what it means to know, to measure, and to describe reality. At the heart of Bohr's approach was the recognition that the microcosm does not conform to classical expectations, and that the rules governing subatomic particles are fundamentally different from the laws of the macroscopic world. This insight transformed physics from a deterministic, mechanistic discipline into one that embraces probability, complementarity, and the intrinsic limits of observation. Bohr's atomic model provided the first concrete framework for quantum energy levels, a concept that became central to quantum mechanics. By showing that electrons occupy discrete orbits and that energy is absorbed or emitted in precise quantum, he laid the groundwork for understanding atomic transitions, spectral lines, and chemical behavior. This principle of quantization was not merely a mathematical tool, it was a fundamental aspect of reality, revealing that nature operates according to rules that differ from classical intuition. Bohr's insistence on connecting theoretical constructs to observable phenomena ensured that quantum theory remained grounded in empirical evidence, even as it explored concepts that defied common sense. The philosophical dimension of Bohr's influence is equally significant. He introduced the principle of complementarity, which reconciles seemingly contradictory behaviors by demonstrating that different experimental arrangements reveal different aspects of the same system. An electron can behave as a particle or as a wave, depending on how it is observed, and both descriptions are necessary to fully account for its behavior. This concept challenged centuries of scientific thought that assumed objective properties exist independently of observation. Bohr showed that in the quantum realm, the act of measurement is inseparable from the properties revealed, fundamentally altering the way scientists think about knowledge, reality, and the limits of description. Complementarity became a cornerstone of the Copenhagen interpretation, a philosophical framework that continues to guide the interpretation of quantum mechanics today. Bohr's influence extended deeply into the culture of scientific collaboration. His institute in Copenhagen became a gathering place for some of the most brilliant minds of the 20th century, including Werner Heisenberg, Wolfgang Pauli, and Max Born. Bohr fostered an environment that encouraged questioning, debate, and the exploration of radical ideas. He challenged his colleagues to examine their assumptions, to consider the philosophical implications of their models, and to embrace the counterintuitive nature of the quantum world. This intellectual climate accelerated the development of quantum theory, enabling breakthroughs that would have been impossible in a more rigid, conventional setting. Bohr's leadership demonstrated that scientific progress depends not only on individual genius but on a culture that values creativity, rigor, and open inquiry. The methodological innovations introduced by Bohr were equally transformative. He emphasized the interplay between theory and experiment, insisting that models must be testable and grounded in observable phenomena. Hypotheses could not exist in isolation. They had to be connected to measurable outcomes. This approach strengthened the predictive power of quantum mechanics and ensured that the field remained empirical rather than purely abstract. By establishing this principle, Bohr helped shape the modern scientific method for dealing with phenomena that lie beyond direct human intuition, demonstrating that conceptual rigor and experimental verification are mutually reinforcing rather than opposed. Bohr's work also influenced the emerging understanding of uncertainty in the quantum world. Although Werner Heisenberg formalized the uncertainty principle, Bohr's insights into quantized energy levels and electron behavior anticipated the conceptual shift toward probabilistic thinking. In classical physics, precise predictions were possible, given complete knowledge of initial conditions. In Bohr's quantum framework, outcomes could only be predicted in terms of probabilities. Electrons do not have definite positions and momenta until measured. Their behavior is inherently statistical. This paradigm shift challenged deterministic assumptions, demonstrating that the fundamental nature of reality is probabilistic, and that certainty is limited in the quantum domain. Bohr's thinking helped scientists embrace this counterintuitive principle and integrate it into the broader structure of quantum theory. Another key aspect of Bohr's influence was his ability to bridge disciplines. His insights connected atomic physics to chemistry, spectroscopy, and emerging technologies. By explaining electron configurations and energy transitions, Bohr provided a theoretical basis for the periodic table, chemical bonding, and the behavior of materials. Spectroscopic analysis, once a descriptive tool, became a precise method for probing atomic structure. The principles he introduced later informed developments in semiconductors, lasers, and quantum devices. Bohr's vision demonstrated that deep theoretical understanding could drive practical applications, revealing the unity of science and technology in exploring and harnessing the natural world. Bohr's philosophical contributions also extended to the interpretation of scientific knowledge itself. He emphasized the limitations of classical analogies, showing that attempts to describe quantum phenomena using familiar macroscopic models often lead to contradictions. Nature, at the atomic level, is governed by laws that require new conceptual frameworks. Bohr encouraged scientists to accept the unfamiliar and to develop intuition aligned with empirical evidence rather than preconceived notions. This approach fostered intellectual flexibility, allowing researchers to navigate the complexities of quantum mechanics while maintaining logical consistency. Bohr's philosophy underscored that scientific progress often requires not just data and equations but a willingness to rethink fundamental assumptions. The debates between Bohr and Einstein illustrate the depth and reach of his influence. Einstein, seeking determinism and objective reality, challenged the completeness of quantum mechanics. Bohr defended the principles of complementarity and probabilistic interpretation, arguing that classical notions of determinism were inadequate for describing atomic phenomena. These debates were not merely theoretical, they shaped the conceptual foundation of modern physics, highlighting the need for a coherent framework to interpret experimental results. Bohr's ability to articulate and defend his ideas against rigorous critique cemented his role as a central figure in the philosophical as well as the technical development of quantum theory. Bohr's legacy also lies in the enduring methodological principles he established. His insistence on testable hypotheses, his integration of theory and observation, and his emphasis on conceptual clarity continue to guide research in quantum mechanics and related fields. Scientists today rely on frameworks that balance abstraction with empirical grounding, a balance that Bohr exemplified. His approach demonstrates that the advancement of knowledge requires both imaginative theorizing and disciplined validation, a lesson that transcends disciplines and remains relevant in contemporary science. Finally, Bohr's influence on scientific philosophy is inseparable from his humanistic approach to inquiry. He recognized the limits of human perception and intuition, yet he believed that rigorous thought and careful experimentation could reveal profound truths about the natural world. Bohr's vision encouraged humility, curiosity, and intellectual courage quality, essential for exploring phenomena that defy everyday experience. By showing that the universe, at its core, operates according to principles that are precise yet counterintuitive, Bohr transformed not only the content of science, but the way scientists think about the act of knowing itself. In essence, Niels Bohr's influence on quantum mechanics and scientific philosophy lies in his integration of conceptual innovation, empirical rigor, and philosophical reflection. He reshaped the understanding of the introduced the principle of complementarity, emphasized probabilistic reasoning, fostered a culture of intellectual collaboration, and provided a methodological framework that continues to guide research today. Bohr's work demonstrates that the evolution of science is not merely a sequence of discovery, but a transformation in the way reality is conceptualized, measured, and understood. His legacy endures as a testament to the power of insight, imagination, and philosophical rigor in reshaping human understanding of the universe. Niels Bohr's legacy in modern science and technology is profound, far-reaching, and intricate, woven into the very fabric of contemporary physics, chemistry, and engineering. His work extended beyond the confines of theoretical models to influence practical technologies, experimental technique, and scientific philosophy, demonstrating that groundbreaking ideas can reshape both understanding and application. Bohr's introduction of quantized energy levels and discrete electron transitions not only transformed the comprehension of atomic structure but also became a cornerstone for technological innovations that define the modern world. From lasers and semiconductors to quantum computing and medical imaging, Bohr's principles underpin a remarkable range of scientific and technological advancements. By bridging theory with practical utility, Bohr exemplified the capacity of scientific insight to have enduring and tangible effects on society. One of the most direct technological outcomes of Bohr's work lies in the field of spectroscopy. By elucidating the connection between electron transitions and emitted or absorbed light, Bohr provided the foundation for understanding atomic and molecular spectra. Spectroscopy, which was once largely descriptive, became a precise analytical tool, allowing scientists to measure atomic properties, identify elements in distant stars, and analyze complex chemical compounds. These methods have since evolved into advanced instruments such as spectrophotometers and mass spectrometers, tools essential in chemistry, astronomy, biology, and materials science. Bohr's principles transformed the observation of light from a passive recording of phenomena into an active, quantitative exploration of atomic and molecular structures. Bohr's insights also directly contributed to the development of lasers. The understanding that electrons occupy discrete energy levels and emit photons when transitioning between states is fundamental to the operation of a laser. Stimulated emission, a concept rooted in quantum theory, allows photons to induce other electrons to emit identical photons, producing a coherent, focused beam of light. Lasers now permeate numerous aspects of modern life, from optical communication networks and medical surgery to barcode scanners and industrial cutting tools. Bohr's conceptualization of atomic energy states enabled these innovations by providing a theoretical framework for controlling and harnessing the behavior of electrons and photons in engineered systems. In addition, Bohr's work laid the groundwork for semiconductors, which form the backbone of modern electronics. Understanding electron configurations and energy bands allowed scientists to manipulate the conductive properties of materials, creating devices such as transistors, diodes, and integrated circuits. These components are fundamental to computers, smartphones, and countless electronic devices that shape everyday life. Without Bohr's pioneering insights into atomic structure, the development of semiconductor technology, and by extension the digital revolution, would have been significantly delayed. His theoretical contributions transformed abstract quantum principles into tools for engineering and industry. Bohr's legacy also extends into nuclear physics. While his atomic model focused on electrons, the broader implications of quantization and energy levels informed the study of atomic nuclei, nuclear decay, and particle interaction. Understanding the discrete energy states of nucleons and the probabilistic nature of quantum transitions allowed researchers to explore nuclear reactions with precision. This knowledge became crucial for the development of nuclear energy, medical imaging techniques such as PET scans, and radiation therapy for cancer treatment. Bohr's framework provided a conceptual map that guided experimental exploration at the nucleus and subatomic particles, revealing a universe governed by discrete, quantifiable rules even at the most fundamental levels. Medical technology has also benefited from Bohr's insights. Magnetic resonance imaging, radiation therapy, and diagnostic spectroscopy all rely on principles derived from quantum mechanics, which in turn are rooted in Bohr's understanding of atomic behavior. By revealing the rules governing electron energy levels, photon emission, and atomic interactions, Bohr's work indirectly shaped the instruments that allowed doctors to visualize, diagnose, and treat conditions with unprecedented precision. These applications demonstrate the societal impact of foundational science, illustrating how abstract theoretical breakthroughs can ripple outward into technologies that improve human health and quality of life. Bohr's influence extends into quantum computing and information science, areas at the forefront of technological innovation. The manipulation of quantum states, superposition, and entanglement relies on principles of discrete energy levels and probabilistic transitions, ideas that Bohr helped establish. By conceptualizing the behavior of quantum systems and emphasizing the importance of measurement and observation, Bohr laid the philosophical and theoretical groundwork for technologies that exploit quantum phenomena. Quantum computers, quantum cryptography, and advanced sensors all trace their conceptual origin to the insights he provided about the fundamental rules governing subatomic particles. Bohr's work demonstrates that theoretical science can anticipate and enable technological revolutions decades later. Bohr's legacy is not limited to practical applications. It also transformed the culture and methodology of scientific research. He championed a collaborative, international approach, fostering an environment where experimentation, debate, and theoretical exploration were intertwined. His institute in Copenhagen became a hub for intellectual exchange, producing generations of physicists who would go on to develop quantum mechanics, nuclear theory, and particle physics. Bohr's emphasis on rigorous conceptual thinking, combined with empirical verification, set a standard for research that persists in laboratories around the world. His influence helped establish the norms of scientific inquiry in the quantum era, emphasizing the interplay of observation, prediction, and conceptual clarity. The educational impact of Bohr's work is equally profound. By introducing accessible models of atomic behavior and emphasizing the importance of both conceptual understanding and mathematical rigor, he shaped how quantum mechanics is taught and understood. Students learn to visualize energy levels, electron transitions, and wave-particle duality through the frameworks he pioneered. These pedagogical tools continue to guide generations of physicists, chemists, and engineers, ensuring that Bohr's intellectual legacy is not only preserved, but also actively propagated. His approach demonstrates the importance of clear conceptual models in fostering comprehension of complex, counterintuitive phenomena. Bohr's insights also encouraged a philosophical reconsideration of the nature of reality and knowledge. By emphasizing that the act of observation affects the phenomena observed, and that quantum systems exhibit inherent probabilistic behavior, he challenged classical notions of objectivity and determinism. This perspective influenced not only physics but also philosophy of science, prompting debates about the limits of human understanding, the role of measurement, and the nature of scientific explanation. Bohr's legacy illustrates that scientific ideas can resonate far beyond their technical context, shaping broader intellectual landscapes and influencing how humans conceptualize reality itself. In essence, Bohr's contributions demonstrate the profound connection between theoretical insight and technological transformation. By elucidating the rules of atomic behavior, quantization, energy transitions, he provided a foundation upon which a multitude of scientific and engineering disciplines could flourish. His work enabled innovations that transformed communication, computation, medicine, and material science. Moreover, by fostering a culture of rigorous, conceptually grounded research, Bohr influenced the methodology and philosophy of science, leaving a legacy that endures in both thought and application. Bohr showed that understanding the microscopic structure of matter is not merely an academic pursuit. It is a gateway to shaping the world in ways that are tangible, transformative, and enduring. Ultimately, Niels Bohr's legacy in modern science and technology is a testament to the power of imagination guided by empirical rigor. His insights into the atom provided the keys to a universe governed by discrete laws, probabilistic transitions, and interdependent relationships between observer and observed. These principles have not only revolutionized scientific understanding, but have also enabled technologies that define contemporary life. Bohr's vision illustrates the profound impact that foundational science can have, revealing the hidden structure of reality and transforming them into tools that enhance human capability, knowledge, and society. His work continues to inspire, reminding us that the exploration of the fundamental rules of nature is both a scientific and a humanistic endeavor, capable of reshaping both thought and the material world in enduring and transformative ways. Niels Bohr's enduring impact on science and human understanding extends far beyond his immediate contributions to atomic theory and quantum mechanics. While his models and principles revolutionized physics, his influence is equally evident in the broader ways in which humans conceptualize reality, knowledge, and the process of scientific inquiry. Bohr's work exemplifies the intersection of empirical observation, mathematical rigor, and philosophical insight, illustrating that the act of understanding nature is inseparable from the methods and assumptions we bring to it. The legacy of Bohr is not merely a collection of formulas or experimental results. It is a transformation of the very lens through which we perceive the universe. His vision demonstrated that reality at the smallest scales operates according to principles that are counterintuitive, probabilistic, and interdependent, challenging long-held notions of determinism and classical logic while opening new avenues for thought, discovery, and technological progress. At the heart of Bohr's enduring influence is his concept of complementarity, the idea that objects in the quantum world exhibit multiple, seemingly contradictory properties that are revealed depending on the context of observation. An electron can behave as a particle in one experiment and as a wave in another, and both perspectives are necessary to capture its full nature. This principle fundamentally reshaped the way scientists approach the microcosm, demonstrating that phenomena cannot be fully described without considering the experimental conditions under which they are observed. Complementarity provided a philosophical framework that reconciled paradoxes inherent in quantum mechanics, allowing researchers to interpret results without abandoning logical consistency. This concept continues to guide scientific thinking today, influencing interpretations of quantum experiments, the design of advanced technologies, and discussions in the philosophy of science. Bohr's insights into the probabilistic nature of reality further cemented his legacy. Classical physics had long assumed that given complete knowledge of initial conditions, the future behavior of a system could be predicted with certainty. Bohr's atomic model and subsequent quantum principles revealed that the deterministic view is insufficient at the atomic and subatomic levels. Electrons, photons, and other quantum entities do not possess definite properties independent of measurement. Their behavior can only be described probabilistically. This recognition introduced a new paradigm in scientific reasoning, one that accepts uncertainty as an intrinsic feature of nature rather than a limitation of human measurement. Bohr's probabilistic approach has influenced a wide range of disciplines, from quantum physics to statistical mechanics, and has reshaped how scientists understand causality, prediction, and the limits of knowledge itself. Bohr's role in establishing the Copenhagen interpretation of quantum mechanics underscores his enduring impact. This interpretation, which he championed, posits that the properties of quantum systems do not exist in a definite state until measured, and that the act of observation fundamentally influences the outcomes. By formalizing this perspective, Bohr provided a coherent framework for understanding phenomena that defy classical intuition. The Copenhagen interpretation has become one of the foundational pillars of modern quantum theory, guiding experimental design, theoretical exploration, and the interpretation of results. Through this work, Bohr shaped not only the content of science, but also the methodology and epistemology by which scientists understand the quantum world. Bohr's influence extends into the realm of education and intellectual culture. His ability to translate complex, abstract principles into accessible models, metaphors, and conceptual frameworks allowed generations of scientists and students to engage with quantum mechanics without being overwhelmed by mathematical abstraction alone. Bohr emphasized the importance of visualization, intuition, and conceptual understanding alongside mathematical rigor. This approach has shaped physics curricula worldwide, enabling learners to grasp the counterintuitive nature of quantum phenomena while developing the analytical skills necessary for research. Bohr's pedagogical legacy ensures that his ideas continue to influence not only scientific discovery but also the way future generations are trained to think about and explore nature. The practical ramifications of Bohr's work further solidify his enduring impact. His principles underpin technologies that define modern life, from laser and semiconductors to magnetic resonance imaging and quantum computing. Understanding quantized energy levels, electron transitions, and the probabilistic nature of quantum systems has enabled the creation of tools and devices that transform communication, medicine, computation, and industry. Bohr's theoretical insights, once abstract and seemingly distant from application, became the foundation for innovations that permeate everyday life. This bridging of theory and practice exemplifies the unique power of fundamental science, the ability to reveal hidden structures of reality and transform them into technologies that enhance human capability and understanding. Bohr's collaborative and mentorship practices further amplified his impact. His institute in Copenhagen became a hub for intellectual exchange, where some of the most brilliant physicists of the 20th century, Heisenberg, Pauli, Born, and others, debated, refined, and expanded the ideas that form the foundation of modern quantum mechanics. Bohr encouraged rigorous debate, philosophical reflection, and creative theorizing, fostering an environment in which groundbreaking discoveries could flourish. The culture he cultivated emphasized the synthesis of intuition, experiment, and theory, establishing a model for scientific communities that remains influential. Through mentorship and collaboration, Bohr ensured that his insights would propagate across generations, embedding his conceptual vision into the very fabric of scientific practice. Bohr's work also influenced broader philosophical and ethical reflections on science. By demonstrating the interdependence of observation and reality, he challenged conventional notions of objectivity and determinism. His ideas prompted discussions about the limits of human knowledge, the role of measurement, and the ethical responsibilities of scientists working at the forefront of discovery. Bohr himself was deeply involved in public discourse on science, particularly in the context of nuclear physics and the ethical implications of atomic energy. His perspective emphasized that understanding and technological power must be coupled with reflection and responsibility, a lesson that remains relevant in contemporary debates over scientific advancement and its societal consequences. The debates between Bohr and Einstein illustrate the depth and reach of his influence. Einstein's objections to the probabilistic interpretation of quantum mechanics, his insistence that God does not play dice, highlighted fundamental philosophical differences about the nature of reality. Bohr's articulate defense of complementarity and the Copenhagen interpretation demonstrated the robustness of his conceptual framework and its ability to accommodate experimental evidence that defied classical expectations. These debates, which spanned decades, not only shaped the development of quantum theory but also illuminated the interplay between science and philosophy, showing how foundational principles can have far-reaching implications for understanding the universe and humanity's place within it. Bohr's enduring impact also lies in his demonstration that scientific inquiry is a human endeavor, shaped by imagination, curiosity, and collaboration as much as by measurement and calculation. He showed that progress emerges from the interplay of theory, observation, and philosophical reflection, and that scientific knowledge evolves through dialogue, critique, and conceptual innovation. Bohr's legacy reminds us that the act of understanding nature is inseparable from the frameworks we construct to interpret it, and that the power of science lies not only in prediction and control but in deepening our comprehension of reality's underlying principles. Ultimately, Niels Bohr's enduring impact on science and human understanding is multifaceted and profound. His insights into atomic structure, quantum behavior, and the probabilistic Nature of reality reshaped physics, chemistry, and technology. His philosophical contributions, particularly the principle of complementarity, challenged classical assumptions and influenced the interpretation of scientific knowledge. His mentorship, intellectual leadership, and pedagogical innovations propagate his vision across generations, shaping both research and education. Bohr's work bridged the theoretical and practical, the conceptual and technological, leaving a legacy that continues to influence contemporary science, philosophy, and human understanding. By revealing the hidden structures of matter and the subtle rules governing the quantum world, Bohr transformed how humanity perceives the universe, demonstrating that the pursuit of knowledge is both an intellectual and a profoundly human endeavor, capable of reshaping thought, technology, and society alike.